All right, let's talk about kinetic energy and how it applies to work. So, whenever we talk about anything with that KINE prefix, right? Kina, we saw it in kinematics. You see it in terms like kinesiology. Well, kina is just Greek for motion, right? And so, kinetic energy is the energy that is present due to the motion of an object. So, anything that has mass, anything that is moving, will have kinetic energy, right? So it doesn't matter how small that mass is. If it's moving, it has kinetic energy due to the fact that it's moving. So even say take an electron. An electron has a tiny, tiny mass, but what's it doing in that electron cloud? Well, it's buzzing around, right? It's moving, right? So even something as small as an electron has kinetic energy due to the fact that it has mass and it is moving. Now, energy, all types of energy, are also going to be measured in joules. And that'll become important here when we relate work to energy here in just 1 second. So take a look at the equation, right, where k equals 1 half mv squared. So v is your velocity in meters per second, m is your mass in kilograms, and k is your kinetic energy. Now, obviously, increasing the velocity of an object of constant mass will change the kinetic energy a great deal because of that squared. Now also think about this. Whether the velocity is negative or positive, what's going to be true about your kinetic energy? Well, because velocity is squared, your kinetic energy is always going to turn out positive, which means that kinetic energy is a scalar quantity. So let's take a look at that first example in the notes, where we've got a Boeing 747 airliner weighing at 2.2 times 10 to the 6 newtons. And again, watch language when you're reading through these problems. There's a big difference between massing and weighing, right? Weight is the force of gravity, mass is how much stuff it's made out of. Is cruising at a ground speed of 268 meters per second. Compute its kinetic energy. All right, let's go ahead and just start by listing out what we know. Well, we know that the weight of the object, the airliner, is 2.2 times 10 to the 6, which means, right, if weight is equal to mg, its mass would be 2.2 times 10 to the 6 divided by 9.8. Which would be 224,400 and we'll round to 90 kilograms. All right, so again, that's where most people would have messed up this problem, is not realizing that they gave you weight and not mass. We know that it's cruising at a speed of 268 meters per second, and we want to know kinetic energy. All right, so let's plug that in. Kinetic energy is 1 half mass times velocity squared. So kinetic energy is 1 half of 224,490 kilograms times 268 meters per second squared. And again, make sure you're always in meters per second when you're calculating out kinetic energy. And that comes out to roughly 8.1 times 10 to the ninth joules. Right, and that might seem like a huge number, but think about what you're dealing with. You're dealing with something with a huge mass moving at a very fast velocity. That's roughly 600 miles per hour. So you would expect something with that much mass moving that fast to have a ton of kinetic energy present within it. Now they ask us if 1 kilogram of TNT yields 4.6 times 10 to the 6 joules, how much TNT is the plane's kinetic energy equivalent to? Well, this would just be a simple matter of dimensional analysis. So 8.1 times 10 to the ninth joules. And we know that 1 kilogram TNT is equivalent to 4.6 times 10 to the 6 joules. Then that roughly comes out to 1,753. 1,753 kilograms of TNT. All right, so remember again, you can always use dimensional analysis if you're given any sort of ratio comparing two things. Now, one thing to keep in mind also is that think back to when we talked about relative motion at the beginning of the year. We talked about motion being relative to the observer, right? Well, it's the same thing with kinetic energy. Kinetic energy is relative to where you're setting your observation state as. So, for instance, if you're sitting next to a glass of water on a train that's moving 60 miles per hour, well, relative to you, that glass of water isn't moving, right? So, relative to you, that glass of water has 0 joules worth of kinetic energy. But to someone outside standing on the tracks, observing that glass of water go zooming by them, well, they see that glass of water moving at 60 miles per hour down the track, right? So, relative to that stationary observer on the track, that glass of water does have kinetic energy. So, kinetic energy, just like velocity, is relative to the observer. But again, when we're talking about energy, and we'll get into this when we talk about potential soon, we're not really interested in a firm exact number because, again, everything is relative to your observer. What we're interested is in differences in energy, right? Energy differences between point A and point B. Now, we talked a little bit about work being a change in energy. Well, that brings us to the work energy theorem, where your net work done on an object will change the object's kinetic energy, right? So, net work is equal to a change in kinetic energy, which is your energy final minus energy initial. So basically, what the work energy theorem tells us is that if work is done on an object, its kinetic energy changes, right? So if, let's say, you've got a box that's sliding down a hallway and there's a frictional force doing work on it. Well, that frictional force is going to change its kinetic energy, right? It's going to bring it to a stop. Now, this has a lot of kind of common ground with um, the impulse momentum theorem that we talked about last unit in momentum. Think about, say, let's go back to the fastball pitcher we talked about in the impulse momentum theorem. If you can apply a constant force over a huge distance, you can change the kinetic energy to a much greater degree, right? And that's why your fastball pitchers are typically taller guys with longer wingspans, right? They apply that force on that baseball over a greater distance, thus changing the kinetic energy to a maximum level, right? Same thing with that frog example, right? The frog with the long legs. Well, why does it have that? Well, that frog is able to exert a force over a great distance, changing its kinetic energy to the max. So you'll see a lot of similarities there with the impulse momentum theorem and the work energy theorem in terms of concept. But let's take a look at an example here. So in the notes we got, according to the record books, Alexander Zaz, known as Samson, would, when he wasn't bending iron bars, catch a 104-pound woman, which is 463 newtons. Again, notice newtons, they've given us weight, not mass, fired from a cannon at around 45 miles per hour. Assuming that Samson brought her to a rest uniformly in a distance of 1 meter, compute the average force he exerted on our heroine. As a guess, take her landing speed to be 8.94 meters per second. So basically what they're saying is she's fired out of the cannon at 45 miles per hour. We don't care about that number because what we care about is that landing speed. So basically what they're saying is the landing speed is 8.94 meters per second. So she's going 8.94 meters per second when he catches her, and he brings her to a halt over a distance of 1 meter. And so we want to know the average force he exerted on her. Well, flip the paper. Let's start with our knowns and unknowns. The initial velocity of the lady is 8.94 meters per second. The final velocity is 0. This all occurs over a distance of 1 meter. And we want to know F, that average force exerted. And again, when we're looking at the work energy theorem, that F in there is an average force, right? It's not a force that's going to be fluctuating. It's going to be an average force for our purposes. All right, so work is a change in kinetic energy, right? Or final minus initial. So your work would be 0 minus 1/2 mv naught squared, right? Your final velocity is 0, so your kinetic energy final is 0, and your initial kinetic energy is going to depend entirely upon your initial velocity. And again, we can substitute in FD for work. And we can start plugging in our values. Although before that, we're going to need to know the lady's mass, right? They gave her our weight. So mass would be force of gravity over g, which would be 463 newtons over 9.8 meters per second squared. So the mass of the woman is 47.2 kilograms. So 47.2 kilograms times your initial velocity of 8.94 meters per second squared. So your force here comes out to negative 1886.2. Right, and it's negative because it's in the direction opposite the positive direction of travel. Now, you can make your life even easier here by just deriving your equation a little bit. So if we got work as being a change in kinetic energy, and that's equal to your final minus your initial kinetic energy, well, think about what you're looking at. You're looking at 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. So you can always set work equal to 1/2 of the mass times the difference between the square of both of your velocities. So really, deriving your equation further really makes your life easier because you don't have to do as much of the mathematical work if you derive from here to here and then just plug in your v squared and v naught squared values. So it's always a good tip is you want to derive equations, make your life easy. Now, we'll be talking about potential energy here next time. I'm going to be putting up a set of very basic questions dealing with the work energy theorem. I'll also be putting up a daily problem that will be for an individual grade. Now, for those of you who are new, keep in mind that everything is for a grade to somewhat extent. So all of the practice work we do, so everything in Google Classroom that just says for practice, submit when complete, all of those are averaged into one final summative grade, or sorry, formative grade at the end of the quarter. So make sure you're keeping up with the practice work, submitting those. But again, I'll put up a daily problem, which will be for its own individual formative grade here early next week, because we're still trying to set up the grade books. But yeah, I'll see you in the live sessions if you got any questions, and have a good one.